Hello everyone. In this video, I'm going to talk about borides. So we all know that boron is one of the most useful and versatile elements in the earth. It is very useful to serve purposes in our everyday life. Suppose if we consider this mixer grinder, the blades here, it itself has some boron coating and borides maybe, and it is one of the hardest substances in the earth known, boron and its elements. So this lock, even it has boron coating, having steel. It is basically stainless steel, but the coating over these compounds, over these materials of boron, and this lock. So these things are very much importance in our everyday life, and even this badminton racket also, and tennis rackets most probably. Lawn tennis rackets have boron coatings all over it. So today we are going to talk about borides. Borides are compounds which are composed of boron and connected with less electronegative elements. So we will be basically dealing with metal-rich borides and their structures and the basic preparation of borides. There are small-scale preparation and large-scale preparations. So we will see this in detail. So, borides are compounds consisting of boron and less electronegative elements. Most borides are metal compounds whose general formula is MXBY, where B is negatively charged. Borides are produced by melting or sintering metals with boron. Electropositive metals like alkali metals form borons that are rich in boron, for example, Mb2. Metals that are less electropositive, such as iron, form borides that are rich in metal like M2B. This is why borides can take many forms, and structures of boron can be isolated or branching out to form strings and layers. Sorry. So we will first discuss about the properties of borides. Borides are extremely hard, or we can say they are refractory. They may be as hard as diamond. They are conducting in nature. They have high melting point, which can be more or less equal to 3000 degrees Celsius. M plus B which is a general reaction of metal borides. M plus B, where M can be any metal, on extreme high heating. Borides are formed on at extreme conditions because they are very difficult to make and can be obtained in least purest form. So we have to heat them at very high temperatures. The metal borides, their stoichiometry ranges from M5B to MB66. Borides, here I have written the definition of borides, which are compounds consisting of boron and less electronegative elements. Within borides, we can also study boron carbides, in which have the formula M4B, B4C. Borides, they have extremely high mechanical properties. They are extremely hard and is used as a perfect material for steel hardening. That is what I showed you. These things, they are basically made of steel, but to harden them, it is made with the help of borides. Steel hardening and boronized steels are therefore less prone to corrosion and wear. Borides have a very high melting point, giving them great heat. Of enhanced stability and resistance is also very high. They possess excellent electric conductivity and chemical stability against acids and bases. So borides have very much importance in our daily lives also. We will see about the applications of borides later on. First, we will see the reactions of borides. These are the small-scale laboratory preparations of borides. First reaction is chromium plus Nb upon extreme high heating, 1150 degrees Celsius. We get CrBn, chromium borides. This is the direct combination of elements, most widely used technique. Second is the reduction of this. It is the most widely used technique for preparation of borides. Second is reduction of metal oxide with boron. Scandium trioxide on heating with boron will get scandium boride. Since there are a lot of temperatures and we don't have to remember all this, so I just gave a symbol of a heating sign. Third is The co-reduction of volatile mixed acids with hydrogen using a metal filament, hot tube or plasma torch, etc. So this is the reaction. We get titanium boride, and remember this compound titanium boride has very much significance in nano composite materials, materials such as pumps, cutting tools, etc. And it is also biocompatible. And the fourth reaction, in which small scale reaction is for small scale reaction, are reduction of BCl3 or any boron trihalide with a metal. So this is the reaction. These are the commercial methods for the preparation of metal borides. So first one is the electrolytic decomposition from fused salts. This is particularly effective for Mb6 type of boron compounds, which we will study. And for such borides, the metals are molybdenum, tungsten, iron, cobalt, and nickel. Second is a co-reduction of oxides with carbon at temperatures up to 2000 degrees Celsius. V2O5 plus B2O3 gives with carbon, so it is a co-reduction process. Third is reduction of metal oxide with boron carbide. Here B4C is the boron carbide which is used, and we get their corresponding borides. And the fourth reaction is co-reduction of mixed oxide with metals in a thermite type of reaction. This is a thermite type of reaction which is particularly used in alumina and for oxygen, which is used in that railway tracks. For those type of reactions, the reaction is similar to that. Here we use molten sodium. So now we study about the structures of borides. For metal rich borides, there are isolated boron atoms. These are surrounded by metal atoms. So here this boron atom is surrounded all over by these metal atoms. This kind of boron catenation occurs in metal rich borides. So we see this type of catenation only in metal rich borides. So here are certain structures I have drawn. It is of the type M5B, M3B2, MB type, M11B8. M11B8 is only one example is there, ruthenium 11B8. Ruthenium 11B8, and although it does not satisfy the structure, but the ratio is similar to that within M5B and MB66. So this falls under chain type of structures. Then we have double chain type of structure, then honeycomb type of structures, which is M3B4 is a double chain and MB2 is a honeycomb type of structure. Now we come towards the application of borides. Magnesium diboride MgB2 works as a superconductor at 39 Kelvin. It is also used in MRI and NMR. It is magnetic resonance imaging, and NMR is which we use in spectroscopy, nuclear magnetic resonance. Titanium diboride, zirconium diboride, chromium diboride are used in turbine blades, combustion chamber liners, rocket nozzles, etc. Boron carbides and beryllium borides are used to make bulletproof protective clothing in bulletproof metal protective clothing and in protective armor of aircrafts. Here we have one of the preparation of fibrous boron carbide. Here it is the preparation of a boron carbide. 4 BCl3 plus 6 H2 plus carbon fibers, which we call is the carbon yarn, on high heating gives B4C, which is the boron carbide, which are of fibrous form and fibrous forms. It is inert to hot, acid and alkali because of very high tensile strength and elastic modulus. It is used to make military or commercial aircrafts, space shuttles, etc. Also used to make golf shafts, tennis rackets, which I already told you about the badminton rackets and those, bicycle frames, sandpapers, brake liners, clutch, and the oil which we use make them hard. So in the clutch of cars also it is made. Thank you.